Swayam Prabha. Digital India. Educated India.
So in the last class, I was telling about extraction, also known as solvent extraction or liquid extraction, which involves 3 species, and then we talked about how to represent a single phase mixture consisting all the 3 components in a ternary diagram using an equilateral triangle, and also we looked at how to find a composition of a given point in the phase diagram. But in the context of liquid extraction, we said that the original solution is made into direct contact with the solvent, and then the mixture will phase separate into 2 immiscible phases. Okay, so then we are talking about ternary systems in 2 phases. Okay, so the last class discussion was about 3 component system in single phase, but in the context of liquid extraction, we are talking about 3 component systems existing in 2 phases, 2 liquid phases. And that basically brings us to a ternary system with at least 1 pair partially soluble. Okay, so what we mean by that is this component C, this is basically the solute, this is soluble in component A and component B in all proportions. Okay, the solute C is soluble in component A and component B. Component B is the original solvent, component B is the foreign solvent that is added to effect the separation. So in both A and B, C is completely soluble. However, the species or component A and B, these are only partially soluble, and it happens that if you mix A and B, it will phase separate with a small amount of B existing in A and small amount of A existing in B. Okay, so basically we mean that this will lead to a phase separated phases with A rich phase and B rich phase. When we say B rich, we mean that the mole fraction of A is very large and it will have very little amount of B. Similarly, in B rich, the component B will be in majority and component A will be in very small quantities. I am talking about a binary mixture of A and B. Okay, so that is what we mean by partial solubility. Now we could say, like, are there some experimental system that shows this kind of a behavior? I can give a few examples. So if you consider water, chloroform, and acetone. So this is one example where acetone is soluble in water and chloroform separately at all proportions. However, water and chloroform, they are partially miscible to each other. Another example, benzene, water and acetic acid. So in this ternary mixture, acetic acid is a solute which is soluble in benzene as well as water at all proportions. However, benzene and water, they are immiscible, but they have a very small amount of mutual solubility. Okay, so you can think of these as an experimental system that show this 1 pair partially soluble. Okay, now such mixtures can be represented in this kind of a ternary diagram. So you can see that this vertex here is pure component A, this vertex is pure component B, and this vertex is pure component C. Now this baseline AB is a binary mixture of A and B. Now if I take a mixture, if I prepare a mixture corresponding to point J, right, so that would be a binary mixture of A and B, you will see that it will immediately phase separate into two layers. One will be rich in A corresponding to point L, and another one corresponding to point K. So this point K is B rich phase and point L is A rich. Okay. So that is one feature. So let's write this in the baseline AB, which is a binary system. We have not introduced component C yet. It's just a mixture of A and B, both are solvents. And the given example, A and B can be water and chloroform, or it can be benzene and water. Such systems, if you mix corresponding to point J, a mixture at composition denoted by J, this will phase separate into A rich phase, which is point L, and B rich phase. This corresponds to point K. Now let us say we add the third component C. Then depending upon the amount of C that is added, you may have either single phase consisting of all the three components, or you may still have two phases consisting of all the three components in both phases. Okay. So then we can think about what is called a solubility boundary or a binodal solubility curve, which is shown by the red and blue curve. Okay. So the curve LRPEK, okay, that envelope that you see, that is called binodal curve, or this is also known as solubility curve. So outside this curve, outside this binodal curve, all component will exist in single phase. Within this binodal, is a two phase region. So why is that? In some composition they exist in single phase, in other composition they exist in two phase? That's because of thermodynamics. The mutual interaction between all the three components will dictate the overall free energy of the system, and the free energy may be minimum at a single phase composition, or it may split into two different compositions. So everything is determined by the free energy, which comes from the enthalpic and entropic components, which again depends on the chemical makeup of the solute in kind. Meaning that whenever I talk about ABC system, there is a corresponding solubility map, there is a binodal curve. We cannot use one data for another system, okay, they are very much chemically dependent. So that is one thing that will be kept in mind. Now you can see what happens if I prepare a solution inside this envelope. Okay, so let's say I have point M here. So I prepare, I mix A, B, C in certain quantities such that the composition corresponds to point M. Okay, so that's the overall mixture composition. However, since this is lying within the binodal, it will phase separate into two equilibrium phases. One that corresponds to R here, another one corresponds to E here. Remember, when I talked about the line AB, in the absence of C, the phase separation is happening at L and K. But now I have added some third component, component C is added, so that we are now not in J, but we are at M. And this phase will phase separate into two phases. This R here is rich in A, and E is rich in B. In both R phase and E phase, all three components are existing. A, B, C, all of them are existing, but only we are saying that the amount of A present in R is more than the other two components. Similarly, at point E, the amount of B is rich compared to other two components A and C. So now this a line that connects R and E. So let's write this. R is a rich phase and E is the B rich phase, and this would be equilibrium phases. This is resulting from a composition corresponding to the mixture composition at M. Now the line that connects R and E, we call that as a tie line. The line RE, this is called the tie line. You can kind of relate this to any other mass transfer problem, such as let's say absorption or distillation, where there is an equilibrium between a component in two phases. Okay, let's say if you take absorption, a solute is distributed between a liquid and a vapor, and then there is a corresponding equilibrium compositions at the vapor phase and in the liquid phase. The same way here we are talking about an equilibrium of two liquid phases and the corresponding compositions. Okay, the line that connects these two, we call it as a tie line. Now there could be infinite number of tie lines depending upon where this point M is. Okay, for example, there is another line I have drawn here. If I make a composition at some N here, it will also phase separate into two insoluble phases, A rich and B rich, two phase mixture, and you can have any number of composition in between. Now one thing you can note is that as you move from the line AB to the top, you are actually increasing the amount of C. Okay, as you increase the amount of C, you see that these two curves are actually coming closer to closer. Okay, meaning as you add more and more C, it actually acts as a mediator to make both A and B soluble. Okay, so beyond certain C, all of them are actually single phase. Okay, so any point if you take outside this envelope, there is a sufficient amount of C present so that all three components can be in one single phase, again dictated by thermodynamics. Now there is one point P which is called a plate point, where the two phases have the same composition. If you take any point below that, these compositions are different. Okay, but if you keep on going up at some concentration here corresponding to point P, the A rich layer, B rich layer basically converges. This is like a critical point that we know in single component systems, where the existence of a vapor and liquid phase vanishes. They are all like a single phase mixture. The same way here, the A rich and B rich will have the same composition at point P. Okay, we call that as a plate point. Where the composition of A rich and B rich phases are same. From the distillation parlance, you can think this is like an azeotropic mixture. Okay, where both vapor phase and liquid phase will have the same composition of the solute. The same way here, the composition at point P is same for both layers. And another point you might note here is that when you look at the tie line, the tie lines are not horizontal. Okay, what would it mean if it's horizontal? Yes, if the lines are horizontal, it means that the composition of or the mole fraction of C is actually same in both A rich and B rich phases. Okay, so that means that there is no phase separation, because the composition in the original solution and in the extracted solution, they are the same. So generally you want the line to be either positively curved or negatively curved. In this example, the tile lines are positively curved, which means the C distributes more in the B rich phase compared to A rich phase. This is not always the case. Sometimes you may have a line that changes the slope to a negative way, so that a C will be distributed more in the A rich than in B rich. Okay. Again, everything is determined by thermodynamics of the system. So, in some composition, the slope also can change. It is not necessary that the slope will be constant or it is going to be fixed. It has to come from experimental or through thermodynamic calculations. The tile line are drawn. So, at this point, are there any questions? Okay. So, let us move on. So, the one more thing I would like to add here is that even though we say that this is the way to represent the composition of a ternary mixture, single phase or two phase in a ternary diagram, we can also kind of draw an equilibrium line, y versus x kind of a thing, that we use for absorption, desorption and distillation. Okay. So, that basically takes us to slightly a different way of representing the data. So, what you see on the left hand side is the same data that I presented before. Okay. Now, what we are trying to do is, we are trying to map this data into an equilibrium curve kind of a data, where we want to relate the composition, the mole fraction of C in the B rich phase versus a weight fraction of C in A rich phase. So, whatever information that is already there, we are trying to collect it and then put it in a different format, because we are very much tuned to writing y versus x kind of an equilibrium diagram for absorption, desorption and distillation and so on. So, what we are trying to say here is, going back to this figure, that you have a mixture at point M. So, you have a mixture at point M. This phase separates into two equilibrium phases, one that is raffinate, another one that is extract, and there is a corresponding composition. Now, what we could do is, from this one tile line, I can read the value of the mole fraction of C in the E phase and the mole fraction of C in R phase. I can relate those two. Okay. For example, what we will say is that the composition of the mole fraction of C in the extract, we use this symbol Y, and the mole fraction of C in the A rich phase, we call this as X. Okay. So, we are basically denoting the mole fraction of C in B rich phase as Y and X as the mole fraction of C in the A rich phase. So, now what I can do, I can find the value of Y from here. Okay. The Y here is basically the weight fraction of C corresponding to point E. Okay. So, that is somewhere here, this is YE, and then that line is in equilibrium with R phase, and there is a mole fraction of C here, which I call as XR, and the XR composition is here. Okay. So, this XR and YE basically demarks this point. So, this one single point basically denotes this RE tile line. For one tile line, I can read out the composition of the component C in both liquid phases, and then I plot them as X versus Y. So, Y here is the weight fraction of C in B rich phase, and X is the weight fraction of C in A rich phase. So, from each tile line, I read the value of Y and X and I plot Y versus X. So, for this line RE, I find this point. If I look at this point P, at point P, X and Y are the same because it is a plate point. The composition is same in both A rich and B rich phase. So, we find that point P in the 45-degree line. And if you look at along the line AB, where C is 0, so that would be the origin here. Now between these points you can find so many other points. For example, if I take this tie line, I read the y value from here, x value from here, and I make this point. Similarly, if I take this tie line here, I read the y value from here, x value from here, and that basically corresponds to this point. So based on the ternary composition diagram, we can read out the equilibrium values of the two faces and then plot y versus x. Okay. So for any system that shows this kind of a plate point, this curve will always end at the 45-degree line. Okay. Now in this example, the tie line has a positive slope. It is actually a growing slope. Sometimes this tie line can also change the direction. So you see this y versus x curve will probably cross the 45-degree line and come back again. Okay. So again, everything depends on the thermodynamics of the system. So here this particular curve, we call it as a distribution curve. We could very well call this as an equilibrium curve, but I think historically for this particular mass transfer operation extraction, the y versus x curve is denoted as distribution curve. And we also define y star by x as the distribution coefficient. So clearly you see this distribution coefficient is not constant, it depends on the xy value at which you are looking at. So you can actually define the distribution coefficient across the composition range. So probably the distribution coefficient will have a highest value here and it will have a lower value here and so on. So, okay, but it tells you that to what extent component C prefers solvent B over solvent A. Okay, it kind of gives a relative separation possibility. It's kind of very similar to the way we defined relative volatility to tell to what extent the component is more volatile than the other. Okay, so this is also something related to that, and y versus x can be used to find the distribution coefficient here. Now I am going to introduce just one more way of representing this phase diagram. Even though this ternary diagram is very good, the equilateral triangle is a very good place to say that the pure components are very well noted, the binary ternary the two-phase boundary is very well represented. But when we actually do mass transfer operation of extraction, many times the amount of C is never been pure. So amount of C is always less. So we are probably interested in only in the lower part of this plot. Okay, so it makes sense to then rescale this such a way that we are able to change the amount of C. Okay, this one is good, there is no problem with this, it just gives a complete information, but from a practical point of view we may not need to go to very high concentration of C, because many of this leaching many of the extraction problems involve very low amount of C. So we like to kind of rescale this plot such a way that we focus on the phase diagram where the actual operation happens. Okay, and another reason is that so let's look at this without further ado. Let's look at this new way of representing this diagram. So you can see on the right hand side what you see is exactly the same figure I have been showing before, that you can see pure components A, B, C here, and then there is a binodal curve. Here I am using a single color to denote the binodal. Earlier I had red and blue to distinguish between A rich and B rich layer, but now this entire curve is shown in blue. So now what we can do, so this is a equilateral triangle based ternary diagram. We like to do this into a rectangular coordinates unit. So you can see that what we are trying to do here is that we are trying to read the information from the ternary diagram, equilateral triangle based phase diagram, and then map it into a rectangular coordinate system, where in the abscissa or the x-axis we go from pure A to pure B, and here the axis is weight fraction of B. Okay, weight fraction of B in both phases, A rich and B rich. On the y axis, okay, the ordinate axis, we try to relate both x and y. Okay, where again x is the weight fraction of C in the A rich layer and y is the weight fraction of C in the B rich layer. So we use this y axis for both x and y. Let me remind you back again here. So look here. So here we used x and y as an independent axis to draw the distribution curve. So here we are saying that we use the y axis for both x and y. So the way we do that is that so here in the y axis you can actually have C at the pure C at the top. Okay, so you can extend up to the 100% if you want, or you can also truncate it if you like. So ideally we say that this point corresponds to pure C, but you can actually even truncate this diagram somewhere here also if you don't want to go to a high value of high concentration of C. So on the y axis we have x and y, again mole fractions, the range is from 0 to 1. Similarly in the x axis also the range is from 0 to 1. So the way we read this diagram is the following. Let's take again the tie line RE corresponding to this point M. So what we do here is we take this value at E, we read the value. What is the value of component C here? This is YE, okay, because Y is used for the B rich phase, and we read this value of YE, that is right here. This is basically mapped into the mole fraction YE here, and then correspondingly for this point you can find the weight fraction of B at this point. Look, this point is a mixture of A, B, C. YE is the mole fraction of C at point E. At the same point you can find what is the weight fraction of or mole fraction of B also, right? Because it has both A, B, it has all the three A, B, C. I can find what is the weight fraction of B at point E, and using those 2 points I can locate point E here. So this point here is the weight fraction of B corresponding to point E here. Similarly, the tie line actually extends to this point R. Corresponding to R, I find the value of XR because I use X as a unit, X as a variable for the mole fraction of C in the A rich phase, and then for this point R I can also read value of X, the weight fraction of component B. So that would be somewhere here. So using these 2 points I can locate this. So this tie line RE is mapped into a rectangular coordinates. Similarly, I can take another line here, this tie line here. Let's call this as something like F and G. Corresponding to this point, you can find the YG, and then using the corresponding value of weight fraction of B for this point, you can map that point somewhere here. Okay, something like this. So every tie line in a equilateral triangle diagram can be mapped onto a rectangular diagram using on reading the values of X and Y, at the same time we are plotting that in terms of weight fraction of B. We are not losing any information here. Only thing is we are rescaling. The advantage of doing this rectangular diagram is that we don't have to really complete this to full pure component C. We can truncate anytime we want. Okay, sometimes we can truncate even right here if my operation is only below this line. And the extraction problems, most of the times these are solved graphically. I will show some of the examples later on, and because of that we would like to have more expanded graphics at this operating region. So it's good to, mostly we will use rectangular coordinates and do graphical calculations for estimating solvent requirement, number of stages, and other design problems. And the one last point I want to make about the solvent. So solvent, as I said, is something that we choose. We choose a solvent so that the component C could be transferred more easily in large quantities, and we can define something called a selectivity from the solvent point of view. Okay, so with regard to selection of solvent, there are several things to take care of: cost, corrosiveness, and readily availability, environmentally friendly. You know, these are all many things that we have to take care. But above all, the most important things from the separation point of view is that it should selectively remove more C. Okay, that's what is more important. So we could define what is called a selectivity, and this is related to the solvent choice. So when you choose a solvent, you basically find what is the range of selectivity values, and then choose based on higher selectivity. So this is basically defined as weight fraction of C over weight fraction of A in the extract over weight fraction of C over weight fraction of A in the raffinate. So this weight fraction of C in extract is something that we denote as YE, and weight fraction of C in the raffinate is something that we define as X. So this basically brings us to weight fraction of A in the raffinate over weight fraction of A in the extract. So I think a symbol B is used. So you can see that this definition also depends on the composition in question. What is the value of X and Y at that particular operating point? So that means we are not talking about a single value of B, but we are talking about a range of values of B. And I think the way you can calculate this is by looking at what is the feed composition and what is the what is the raffinate composition that you need, what is the extract composition you need. Over that range of composition, you should find the beta value. Okay, for example, if you say that I have a feed consisting of 50% of component C, and let's say you want to reduce that to, let's say, 10% of C. So in that concentration range, you find what's the value of B, and then when you choose your solvent, for those solvents you find beta over those range of compositions and then make a choice. Okay, so like I said, this distribution Y and X is not always an increasing function or decreasing function. You can also have little unusual dependence. So it is important to know for what range of compositions we are calculating this selectivity for the solvent. Okay, so let's just quickly review what we have done here. So from the design or the operation point of view, the extraction is very similar to absorption stripping. Okay, but key difference comes because of the fact that it's a ternary system and we have to deal with fluid mixtures, liquid mixtures that contain 3 component systems. Okay, so that is a key difference with respect to other mass transfer operation. That's one. Now this basically manifests in how we represent the compositions in an equilibrium diagram. So here the equilibrium phases are denoted in a ternary diagram coming over here. So here you can see that the 3 component mixtures are depicted in a equilateral triangular diagram where both phases are shown. The red line here shows the boundary of an equilibrium phase which is rich in A. The blue line corresponds to equilibrium liquid phase rich in B. Okay, any mixture that you bring in below this envelope will phase separate into A rich and B rich phase. In terms of operation, what we would do is we will take a feed mixture that is predominantly A and C. So somewhere along this line you will have the feed, okay, and this has to be contacted with a pure B. Where is pure B? Pure B is somewhere here. This apex here is pure B. So we need to connect this point to the feed composition somewhere along this line AC. If that line happens to be below the envelope, then you know that it's going to phase separate. If it's above that envelope, it is going to be a single phase mixture, no separation, okay, because it's going to yield a single phase mixture. So the question of how much solvent to use and what is the feed composition, all that will have to be chosen such a way that we make use of the two phase boundary, okay. So that is going to be the important thing in the design point of view. One point I want to add further here is that it is not a single way that we can represent the compositions in a ternary diagram. We can also read the equilibrium values of the two phase mixture into something called a distribution curve relating y versus x, where y is the weight fraction of C in B rich layer and x is the weight fraction of C in the A rich layer, in a similar way that we write equilibrium curves for absorption, distillation and so on. And finally, I mentioned that this ternary diagram can also be mapped into a rectangular triangular diagram, so that it has an advantage that I can readjust the composition ranges to different levels of C. I can go to very high C or I can keep it at a very low C, and every tie line that here is mapped here, you do not lose this information of tie line, okay. Whereas in the distribution curve, we do not have an information of tie line, we know only the composition corresponding to tie line, okay. So that means there is some amount of information is lost here, but here we are not losing any information, we are only rescaling it. You will see that this curve changes the shape because of how we choose to plot these two functions, okay. And finally, among other factors with regard to solvent choice, the important one is to find out this selectivity defined as the distribution coefficients, okay. This y by x is basically the distribution coefficient, time how much amount of A is present in the raffinate over how much amount of A is present in the extract. So here again we are saying that A is slightly soluble in B also, that is why in the extract some amount of A is present, okay. So based on this we calculate the selectivity and then choose a solvent, okay. So these are all the introductory material I want to discuss with regard to extraction. Moving forward, I will introduce few operations: single stage operation, multi-stage cross flow, multi-stage countercurrent flow, where the two fluids are mixed, feed and solvents are mixed, and then extract and raffinate are removed. And again we ask the question like, you know, how much solvent to use, how many stages we need, etc., etc., okay. Subsequently, I mean, this is a very beautiful and interesting chapter on itself, but in view of time I am not able to cover many other things. For example, we could also define all these variables in terms of solute free bases. We can also write in terms of a ratio of the weight ratios instead of weight fractions, okay. So many things that we did in absorption and stripping can also be done here, but this course is very highly packed with so many other master operations. So we will keep it in a very minimal way. From the gate question point of view, we do not see much questions coming from this chapter in gate, mainly because the calculations are graphical, okay. Now gate exams are computer based, so many times we are not able to do that. So if you look at gate questions, even though there are very few, they mostly ask you to find out what is the distribution coefficient, what is the selectivity, given a point in the phase diagram, what are the compositions, or given the composition where the point would be, okay. So mostly done from a qualitative point of view, but for this course point of view, we will do some design problems, okay. So with that I will stop here, and we will meet in the next class.